take it away, Safeeq.
Thanks, Malika. Yes, so as Malika said, I am Safeeq Khan. I'm a Cooperative Extension Specialist located here at UC Merced. And I'm also an adjunct professor in the Department of Civil and Environmental Engineering. The title is not very descriptive. It's Watershed Management, so I can talk whatever I want. But I do have some of the, sorry, the screen wasn't moving for a minute. But I do have a brief outline that I would like to follow during this webinar. So I briefly like to talk what are the changes in our climate and forested water landscapes that really warrant the forest management or watershed management, so to speak. And talk about those of the future and in particular how and where climate change will affect downstream water supply. That's really a big question, and everybody is working it. So I'm hoping there will be good interest on that topic. Then moving on, some of the solution side, talking about what's the role of vegetation when it comes to predicting the future, as well as the potential for using the forest management for mitigating and adapting climate change. So jumping on, just to remind myself and remind everyone, this is a very familiar figure that you get to see every climate related. And this is specific California. What we are looking here is historical changes with respect to normal 1970 to 2000 precipitation departure. This is an sample from 20 GCMs downscaled using MACA technique based on University of Idaho from Nabalu. So what we are seeing in terms of precipitation on your left, there is literally no trend, a lot of variability when we look at the projections at the end of the first century. In terms of temperature, the situation is a little bit different, and that's what I think a lot of the studies are focused on. So we're looking at temperature, depending whether it's RCP 4.5 or RCP 8.5, those are the different emission pathways. At the end of 21st century, we are expecting the temperature to go up anywhere between 2 to 5 degrees Celsius above the normal, which is the average between 1970 to 2000. And you're also noticing a lot of variability from one GCM to GCM, and that's why you have noise around those solid blue and red lines. But I also thought to kind of, since this data was produced early, I think in mid 2000, and we are already in 2020, I thought, let's just plot the historical observations and see how close these future projections are actually following in terms of the observations. And those, the gray dots are actually showing the observation, and you can see that the overlapping time period right here, we are pretty much following the upper end of the temperature projection. So we are not really, following the mean. So in fact, the alarm GCM, so to speak, the GCMs that are predicting a much warmer climate by 21st century are better mimicking the observation in this case, which is not really a good, exciting and news to hear. But another thing that I really like to bring into, especially in this seminar, this topic of changing in the forest landscape, that's not really much about as far as the change or the impact related studies. And what I'm showing here is basically changing in forest landscape, both in terms of net forest gain as well as net forest loss. So all the solid Forest Service green colors that you are seeing, those are the places we are actually gaining in terms of net forest. And if we kind of, walk you through, so US is one, and then you see a lot of green spots in Europe, especially in Sweden and Finland, part of Spain. If you go in part of China and Japan, and then part of Brazil. So these are the places where, in fact, there are areas where we are gaining in terms of forest. And a lot of places where we're actually losing. So a lot is happening around our forest that we really need to think and incorporate in all these, change analysis that we are trying to understand and predict what our future water supply is going to look like. So keeping both the climate and forest in mind, and before I get into the research questions, so this is one more. This is a study from Zhu et al. That came out in 2016. What they did basically looked at the trend in average leaf area index as a proxy for forest change, and tried to find out the underlying driver across the globe. And what they concluded in this paper is that almost 50% of the change in the forest, the positive change in the forest, can be explained by climate, as well as the CO2 inflation effect, which is basically the higher atmospheric CO2 in the atmosphere that is facilitating higher photosynthesis, more forest green. And there is about 25% in the LAI is explained by other factors. So those are localized factors that are not related to climate or CO2. CO2 is related to climate, but I'm not sure why they separated the two. I think in this context, climate means change in temperature and precipitation, and CO2 is separate. So almost 75% of the variation in leaf area index can be explained by three drivers: climate, CO2, and some of the local factors. And one of those local factors, especially in the context of US and California, is basically the history of fire suppression. So early 1900, we moved from using fires to basically so we let forest burn. In early 1900 to started actively managing our forest. So we started putting off, fire, and what that did basically, the forest to basically grow everywhere. And as a result of that, what we have now is, our tree density increased by as 40%, and the average basal area has declined by 20%. So we have a lot more trees, but most of those trees are high compared to 1900 or pre-fire suppression. So before 1930, after 1930, this based on this study. So coming back to some of the questions that I would like to touch upon in the seminar is flows of the future, where climate change will affect downstream water supply, and then what is the role of vegetation in predicting flows of the future. And then, what's the role of forest management in trying to adapt to climate change? So I will go one by one and try to answer some of these questions as best as I can. First one, so the main drivers of water supply change is especially in the Western U.S., where we rely much on our snowpack for the dry season water supply, is basically snowpack. So we are, as the temperature is getting warmer, we are getting a lot more precipitation as rain instead of snow. And if we do a comparison across all the Western, so Pacific Northwest, Sierra, Colorado, and Great Basin, what we are seeing is, California is one of the sensitive places across the regions. And if we see increased temperature in California, will lose as much as 10 to 15% of precipitation will fall rain instead of snow. So all these red bars you are seeing on the map will basically decline 10%, 10 to 15% for every degree C increase in temperature. And most of those changes are happening in this mid elevation, what we call additional snow. So very likely that especially in the Sacramento River basin, that we might reach from a snow dominated system to completely rain dominated system by the end of 21st century. And if we do a little bit of comparative analysis, I have to do this, the numbers into perspective. So on average, we get about 34 million acre feet of precipitation as snowfall in California. And that varies between, a warm year and cold year. So in a cold year, you will get about 49 feet. And warm year, you get about 24 million acre feet. So varies a lot, by a factor of 2, in fact. And if you run a simple, sensitivity analysis, you just change the temperature by 1.1, which is, like projections by the end of 21st century. And these are based on not CIMA 5, I believe. So under 1.1 degree C warming, we'll get about 7 million acre feet of precipitation and snowfall, and about 1.8 degree, which is equivalent to RC 0.5 end of 21st century, we'll get about 23 million acre feet, right? And with a 3 degree warming, we get about 17 million acre feet. So if you put the numbers in perspective, 1.8 degrees C warming is very comparable to historical warm episodes, right? So, and this is we're talking about RCP 4.5. We're not even going to RCP 0.5. So it's a very alarming sign as far as our water supply is concerned. The other change that we are seeing is the snowpack melting rate. So we are not only losing the snowpack as most precipitation falls as rain instead of snow, but we are also seeing the snow is melting at a slower rate as opposed to a faster rate, which sounds counterintuitive because in a warmer climate you expect that temperature is warmer, the snow should melt faster. But that's not what we are seeing in the historical observations. And the reason behind this is that as the temperature, get warmer, the snow will start melting at least a couple of weeks earlier in the season when the days are shorter, right? So the temperature is warmer, but it's not getting the solar radiation input as much as if it was melting, let's say, in May or June. So if the snow starts melting in the early or late spring, the days are shorter. That means less solar radiation input. So it makes sense, from the process perspective. But we care if the snow melts faster or slower. We care because it really drives how much of that water is going to go downstream. The snow melts faster, that is going to saturate the soil quickly, generating overland flow or saturated saturation access runoff that might the stream reverse quickly. So it will lead the system faster, meaning that will have less opportunity to use that water for transpiration. But if the snow starts melting slower, that means the water is going to hang around longer, making it more accessible to trees. So it will facilitate evapotranspiration, which means lower stream flow for downstream. So if you look at again, we look at the overall response in terms of the stream flow, and what we are looking here is the historical trend in month stream. So on the left you have January, on the right you have August, and this is the time period from 1950 to 2010. And each chart is one stream gauge, and these are all unregulated stream gauges across the Western US. And these, colors really represent, different quartiles of actual change in stream flow in millimeter per year. So the dots basically showing a decreasing trend, and the green dots, green circles are showing. Sorry, the dark green is showing, an increase in stream flow. So what I'm saying here, we are seeing, places that are more sensitive, there are places that are less sensitive, right? So there are these clusters, red dots, and there are clusters of green dots. But also see that as we move from January to August, we see those clustering shift, right? So the dots that were, or the places that were, not so much sensitive in January became, highly sensitive in August. So what I'm trying to show here is that the stream flow change, or the sensitivity of stream flow to changing climate and landscape, not only varies in space, but also varies in time. So depending, whether you're looking at January or you're looking at August, the answer is going to vary quite a bit. So how can we explain this variation both in space and time? The one way to look at it is if we divide the study based on whether the watershed is actually receiving precip in the snow melt or rain. And these are, again, I just took all those, dots and then basically clumped them based on where receiving, recharge the snow melt or rain, and then start seeing, what is happening across those two groups. So we are seeing the rain dominated warsheds, they show most of decline in January and February, which makes sense. That's when most of the rainfall is happening. And that might be tied to somewhat, reduction in precipitation, historical precipitation, but also slightly warmer wind facilitate a little bit more, canopy evaporation and transpiration. But in a snowmelt dominated system, you see much of this decline is happening in the late spring and early summer. Right, so the timing can be explained by type of precip input, or the variation in timing of the trend can be explained by the type of precip input. And then we can also look at whether the watershed is a fast draining system, meaning that the high drainage efficiency, or a slow draining system, low drainage efficiency. And the way we write the efficiency in a simple term basically means that as the recharge enters the soil, how quickly it will hit the stream. If you have a system that takes less time to convert the recharge into runoff, then water basically will have less time, right, in the landscape, and hence less opportunity for vegetation to eat. So a fast draining system will be more efficient, and a slow system will be less efficient, right? So you can think of like a landscape where you have double network, and it's versus like a volcanic landscape what we have in southern in the Cascades or Northern California, where the stream network not as deep, and that's where the water sticks around longer and accessible by plants. So what we are seeing is that the system is draining slowly, meaning that the water is sticking down lower. Those waters actually show greater decline, twice as much as the high draining or high efficiency waters. So the waters, for example, in southern Sierra, with the granitic rocks, it might be less sensitive as compared to a landscape that volcanic. Simply, because of the differences in the drainage efficiency. So, in that the clustering, we can confirm that there are basically two controls when it comes to changes in streamflow driven by climate. One is the type of input. So there's a rain or snow melt driven system, and the other one is whether it's a runoff dominated system or groundwater dominated system in simple term. Right, so runoff dominated system meaning a high drainage efficiency watershed. A groundwater dominated system means a slow moving water with low drainage efficiency system. So why am I trying to identify the drivers, and what's the motivation behind it? And the reason, it's a long story, but to summarize in a nutshell, we were basically trying to identify key drivers that land managers can actually use to interpret and understand how a landscape A is going to respond to similar level of change in climate as compared to landscape B. And that kind of simple thinking in a simplistic terms, whether it's a snow or vegetation, can help them better allocate resources and better manage resources and manage water. So, for example, by using those filters that I just described, time of input and drainage efficiency, we can actually map out which landscape is most sensitive and which landscape is less sensitive. And that's so this is a live stream flow, and all the yellow basically polygons. This is 6 unit Huck scale. And so all the yellow basically units are the flow is positive, and all blues ones are basically the slow. July strip is not going to change. And we actually also, infer like what's the underlying, driver, whether it's driven by snow or whether it's driven by the geology or it's a combination of the two. He, knows what's driving those changes. And once we have a product like that or things like that, we can actually use something like this, which is currently being used. So this is called a watershed condition classification, and this is what forest managers actually use to dedicate resources where they're going to put the effort in the following reason as far as the restoration is concerned. So all these are basically the color map, the colored region on this map, or all the national forest lands in the US. So all the green polygons, these are again, I believe, on the 6 unit scale. So the green polygons are functioning properly. So that means, you don't really need to do anything. All the yellow ones are function at risk, and then the red one are impaired function. So depending, whether you are going to restore the impaired ones or you're going to up those, I say, those are not really worth investment. So let's just focus on the polygons or the area where, those sheds are falling at risk, because most likely you will be able to restore those to a, functioning properly, category, right? And this classification is based on these indicators, right? So it's based on, what the water quality is, the state of the water quality, water quantity, habitat, and then some of the biological, physical characteristics, there's a road or trail, or there is what type of soil they have, and then, whether it's what kind of fire regime, forest cover, forest health, and things like that. And one thing that you will see is there is no climate in here. So there is no information, as far as the climate sensitivity is concerned, whether any of these polygons will experience any change in the snowpack or not. So what we were able to do with that, the sensitivity mapping and develop or refine the watershed condition, framework into some, what we call the climate informed watershed condition framework. We can use those 12 existing indicators and overlay on top of those. You can have the snowpack sensitivity, where the same HUC units are also sensitive to change in the snowpack, whether the same HUC units where you're going to restore or invest are also sensitive to change in the stream flow. And also, you can do the same analysis for flood, right? And how that can be helpful. So say that if you are planning to, restore or invest in, these polygons where you use asterisks, right? Those are based on those original 12 indicators, but now you have additional information that you can overlay on top of it, and that might help you, move some of those stars, around the landscape where you can see where you can maximize the return on investment. This is one example. And this product has been a success. This is pretty much all the national forest land that I was able to compile, where the forest managers and local NGOs have successfully used those products and to develop what the climate adaptation in these lands will look like. And it continues to started in the, it continues to move upward, and my hope is to bring it southward as because I'm talking to the Forest Service and hoping to develop something similar for California as well. So that was the flows of the future and what kind of data and information we need to inform our management activities around the forested landscapes. Now, I would like to switch a little bit and talk, what's the role of vegetation? Because I didn't talk about the vegetation in that analysis. It's all about climate and to some extent geology. So the vegetation in predicting the flows of the future. In my mind, this is probably the most neglected driver when it comes to predicting, the flow so what's going on there? So just to remind myself and remind everyone, why the vegetation is important. So talk about the climate change, we are basically implying change in temperature, precipitation, and to some extent in CO2. And drivers are changing our hydrologic landscape, right? So they're changing snowpack, they're changing runoff, they're changing transpiration and soil moisture, right? But the same drivers are also changing the vegetation. So the higher temperature can promote, higher photosynthesis. Precipitation is a big regulator when it comes to vegetation productivity and change, and CO2, because a lot of the photosynthesis, photosynthesis is about CO2. So, if you change the atmospheric CO2, that's going to affect how vegetation actually functions in the landscape. So some of these drivers, leaf conductance, is dependent on CO2, distribution of the vegetation and composition, through the range, shift, threshold shift, and also the fire disturbance. We have already seen the massive die-off in the CRS. There's a big question is going to come afterwards. After, and the same question comes after fire. The species are going to come back, or something else is going to take over, because we are not living in the climate under which those species were adapted, right? And then you have disease and pest, then change in the net primary productivity. So there's a lot going on, and the same drivers are changing the vegetation as well as the hydrology. But there's also feedback between the hydrology and vegetation, right? So there is this cyclic loop, right? And we really need to complete this loop. And so far we have been only focused on this arrow when it comes to evaluating climate change impact on hydrology. So this is some of my recent work that I'm trying to to finish. And so the first analysis that we are trying to do here is trying to look at the recent mortality during this 20 and 2010 drought. And this is what we are looking at, basically the tree mortality per hectare. So die-off per hectare. Right, so this is where the peak mortality is happening. This is anywhere between 1,000 meter elevation to let's say 2,000 meter elevation. That's where the die-off is happening. And then if we relate that with the elevation change where our snowpack is changing, there is a strong correspondence between the changing snowpack or the transition snow zone, where we're losing the snowpack, the warm temperature. That's where the trees are dying. And my hypothesis here is that even though there is not much at this elevation, it's a transitional snow zone, so the depth of snow over the season is not that much, but this is a very high productive zone, right? So trees need a lot of water. This is the elevation band where the density of the forest is very, very high. So they need a lot of water to keep the productivity going. So even if it's a small amount of water, the significance of that water is very, very big in the context of forest. So if you lose that water, there is going to be increased competition, and with that there will be increase in stress level. So working on this, and the second analysis that we are looking at is looking at the effect of CO2. So how the CO2 is going to actually amplify or offset the effect of temperature and precipitation. This analysis, what we've done is look at the across the Sierra White by modifying the leaf and the model. So simulated balance, so evapotranspiration, runoff, and soil moisture under RC 8.5. And we're comparing here historic, balance as a function of, RCP, water balance under the RCP 8.5, without accounting for the CO2 feedback. So you see a lot of, variation as a function of elevation. So depending where you are in the elevation, you see in some, as you go higher up, for example, runoff is up, and so as the evapotranspiration, but we don't really see change in the soil moisture. On average, we see each that will likely look by 9%, and the runoff will increase by 15%. And that's simply because more precipitation falls and leaving the system in the winter, right? Sticking around. And the soil moisture likely decline by about %. So this is when you are not accounting for the CO2 feedback. Now you add the CO2 feedback on top of it. What do we see? Again, the same plot. We see no change in ET under the same RC.5, and see a slightly higher increase in runoff, so about 24%, and the soil moisture will go by 9%. So based on the simple analysis, what we can conclude is that the CO2 feedback may likely offset the effect of warming on transpiration, right? So we may not see the level of change in evapotranspiration that we are predicting if we account for the CO2 feedback, right? But change, if even the CO2 to set the of water, we still need to think in terms of what we are going to do for the loss of Snowpack storage, right? Because it doesn't matter, if the precipitation stays the same annual basis, but if most of that precipitation falls as rain during the winter month, they're not really useful for our summer water supply. So Snowpack is, a critical, part of our storage, and we really need to figure out how we are going to make up for that storage loss. So some of the options that I'm involved, we're working on a series of projects trying to look at management alternative to offset some of the storage loss in the form of Snowpack by reducing the evapotranspiration as well as increasing moisture storage, and hopefully if we can figure out the prescription, we might enhance our Snowpack storage and keep that Snowpack longer in the landscape. So that's where we're working on now. The reason behind the emphasis on forest management for additional water supply is if you look at the water balance in California, on average we get about 2 million feet of precipitation, and almost 50% of that is actually lost through evapotranspiration, so about 115 million acre feet. And 75 million acre feet of that out of 115 is through our forest. So our forest really plays a big role in terms of our water balance in the California. So depending whether our forest is using more water or less water, it has a big varying in terms of how much water supply that is available for downstream user. So what happens when you, this is a big question, right? In every seminar you go, you ask what happens, after you take a tree down or take a tree out of the landscape. And the answer is not so easy, in my honest opinion. It's very complicated, process. So what happens, this is the best that I could find, and hope, I was hoping that I might at someday graphic skill will improve and I will be able to draw something that's more representative of our system. But for now, let's work with this. So if you have a landscape that looks like this, and you have all these different hydrologic cycles, transpiration, you have infiltration, stream flow, evaporation, photosynthesis, runoff, right? But if you take a tree out of the landscape, you are altering the transpiration because there are few number of leaves available in the landscape. You might enhance evaporation because now the canopy is open, ground is open, and especially if you have snow sitting around, right? So, and even if you don't have snow, the soil moisture is now open to the solar radiation and open to the sun. You might enhance evaporation. Albedo, not too sure. We might, depending again, it's whether it's a snow-covered landscape or snow-free land. We honestly don't know in what direction the albedo will change, but certainly the albedo will be impacted. The only thing that I'm not sure is the direction. The runoff, because there are changes in transpiration and evaporation, the runoff will change, and so filtration, right? And all of those factors will eventually inflow. Now the question is how much? Because if you are working towards forest management or watershed management, the big question is who is going to pay for it, right? And to answer that question, who is going to pay for it, we need to figure out what benefits that we are getting out of it. And if you can monetize those benefits, only way we are going to monetize those benefits if we can reason accuracy and be able to put right. So that's where a lot of the emphasis right now. But if you go back to the historical, this is not a new topic. You know, people have been studying the effect of forest management on water for like 100, almost like 100 years, right? And this is a paper that came out in 1982. And what we are seeing here is basically, so as streamflow increase, so change streamflow is how much biomass you remove or how the extent of thinning. So changing streamflow is a function of how many trees you take it out the landscape. It's also a function of what kind of vegetation you have, whether it's a cover or whether it's deciduous forest or whether it's a shrub, right? And in most cases we have some combination of of three. But in simple term, if you think about it from the balance perspective, deforestation will increase our yield and afforestation will reduce our water yield, right? The thing that we need to figure out is how much and where. Those are very simple questions, but I hope I can answer those in my lifetime. And I'm being optimistic. So that's on the water quality, water quantity side. The other aspect when it comes to forest management or watershed management is what happens if you take a tree out of the landscape. What happens to the water quality? And this is the data that I really, we don't have any long-term study in California. I managed to pull this data from H.J. Andrews, which is in the Central Oregon, and analyze this last year. Try to answer this question: what happens to the water quality? Are you forest? So it's quite obvious that the inflow will go up, but we are also seeing that as the inflow increases, we also seeing that sediment transport increases, and more so towards the high flow than towards the low flow. So the same magnitude of inflow are producing more suspended sediment than the P-managed forest landscape. We're seeing the same thing in the bed load, right? So same magnitude of peak flow is now producing much higher bed load from the water than a pre-treatment. Right? We are altering by taking a tree out. We are altering these geomorphic regimes. We are increasing the suspended sediment and also increasing the bed load. And we can look at the recovery. What happens, whether it's a, instantaneous thing, like, after you tree out, you manage a forest, the impact will go away in a year, or it's gonna, persist for a decade or two. So we can, this is the nature of the data set. This is a very unique data set. So we can look at the recovery over time. And so this is where, this was the pre-treatment condition, and it was harvested in 1963 and 66. You see it's after the harvest, a sudden increase in both the suspended sediment and bed load sediment. So the red is the suspended, and then the blue is the bed load sediment. So we see a sudden jump, and obviously there's a lot of variability from year to year, depending whether it's a wet year or dry year. And then you see this gradual recovery over time. So the system recovers back. These are, very 1990 was a very different year from the precipitation perspective. There was rain and snow events that caused landslides, so it's not really a representative of the system. But what we can say is 1966 to somewhere around 1990, we can say that the system was back to the treatment condition. But it took how many years? At least like 25 years. More than 25, 26 years. And we are also seeing that if you compare that, this post 2000, time period, we are seeing that while during the pre-treatment period, the system was predominantly dominated by the suspended sediment. So you're not really seeing much bed load coming out of these watersheds, right? But during this, the post-recovery period, the later part of the post-recovery period, we're seeing that it's predominantly, dictated bed load. So there is not much sediment, suspended sediment, in the system that's being transported. So we have gone from a suspended, a fine sediment driven, system to a bed load driven system. So you've changed the entire geomorphic regime of forest management. Okay. Another question that I was interested in, so what happens, what's the driver behind it? So what happens when you take a tree out, you're doing two things. You are altering the, right? You're changing the, the precip input. You're changing the runoff, mechanism. And with those changes in inflow, you're likely going to change the sediments because the sediment transport follows, relationship with the discharge. But while you are, taking the tree out, you're also changing the sediment supply, because it doesn't matter how you do it. If you are walking in the landscape with a heavy machinery, you are going to disturb the soil, right? You are going to create forest shorts. You are going to disturb the undisturbed landscape, right? It's protected by the litter and everything, right? So you're also altering the sediment supply. And so you're changing the stream flow, at the same time you're changing the sediment supply, and those factors are actually contributing to the sediment, the increase or changes in the sediment transport. But which one is? Where should I put money on? Should I care what type of machinery we take in the landscape, or should we care to minimize the changes in the stream flow? Because we need to separate the poor sediment that we can attribute to drivers, right? So without going into the nuts and bolts, how we did it, and there is a citation that if you're interested, you can actually go back and look at it. But what we found is most of the sediment, about 90% suspended sediment and about 95% load sediment, were attributed to increases in supply. So it was attributed to the disturbance in the landscape. And change in flow was only, explaining, 11% of the suspended sediment yield and only 5% of the bed load sediment. Right. So if you're a forest manager, you're trying to manage a watershed, I think your emphasis should be how can we reduce the disturbance landscape, and how can we protect soil in the landscape from the soil perspective, because when you take the tree out, you're also losing the strength, right? The root is no longer holding the soil. So how can you minimize those impacts so that we can maintain the water quality? Because, believe it or not, I mean, yeah, we all talk about the water quantity, but the water quality is as important as water quantity. You can have plenty of water, but if the water is not useful, if the water is not, of a quality that you can use and consume, then it's really not available. So we really need to focus on both water quantity and quality when it comes to watershed management or forest management. So I just like to kind of, plug in some of the projects that I'm working on right now, and I'm hoping that we can replicate the analysis that I just presented, because those data are not from California. Yes, they are similar climate, but I have to admit that California is very different from Oregon, both in terms of precipitation as well as the geology, right? So the soils in the Sierras are very different compared to here. So, I mean, that analysis can tell us something, but if we are going to ignore, then we really need to have our own, study in this region in order to, where should we put money on. These are the three projects that I'm working on right now. One of them is it's called Hemlock Landscape Restoration Project, and these landscapes restoration about 12,000 acre located in the Stennis Forest, where we instrumented 4 watersheds, and we are monitoring streamflow change, we're monitoring the water quality, and in a hope that we will to extract some meaningful information that can help refine some of the management practices. The other project that I'm involved in is the French Meadows project, and it's about 29,000 acres. It's a large forest restoration project. It's collaborative between state, federal, NGOs, and it's a very expensive project. Estimates is coming out anywhere between 1,000 to I believe like the number is somewhere around $1,300 per acre to do the restoration. And the third project that I'm working for last 4.5 years is a more experimental watershed. It's located in the Kings Basin. It's called Kings River Experimental Watershed Project, where basically it's very focused on research rather than trying to restore the landscape. So we are testing different descriptions of management. So we have forest thinning, and have a control burn, and then we have a combination of the forest thinning and control burn. And so we are using some data to for the management questions there. And the idea behind having 3 different projects is basically try to capture the gradient in the Sierras, right? I mean, California is big, and right. So if you have a one data point, that might be questionable, so I'm talking, like extrapolating data from Oregon. If you have one data point in California, and if you're trying to, make sense based on that somewhere in the coast or, somewhere in the north or south, that still, too far apart with very different landscapes and climate. Our hope is that we will be able to do these, 3 different projects. We will be able to capture some of the gradient, both the climate and geology, as well as forest type, and hopefully provide the science that's really needed to do the forest management and restoration. Here's one picture that I really like to show, my audience. So this is on the left is that got restored. So this is a picture of French Meadows project. So on the left, you have a restored watershed. So pretty much all the, the third tree, understory, removed. As I mentioned during my talk, you see a very disturbed landscape, right? So now the question is, what happens to all that loose sediment and fine sediment that's sitting there? Whether it's going to move downstream or is going to resettle there. So big question mark there. The right side of the road, that's the U.S. forest land. I think in Tahoe National Forest, I believe. Yes, it's in Tahoe National Forest, and not treated. So that's how the was originally, and basically we are trying to open the canopy that can reduce transpiration, can potentially store more snow. It can reduce fire risk by cutting the fuel and snag. So this year and the year after, our hope is that the restoration effort will move from land to the public land, because the Forest Service is on board with the project. And let's see whether I'm successful or not, but I would like to play this video just for all the attendees, as well as people who will watch this after this show ends, just to like to show what's really happening in the French Meadows project. So let me know if you don't hear it.
Today we're out in French Meadows. It's an area of the Tahoe National Forest on the American Ranger District. We're looking at a collaborative project that is a landscape scale project with many partners involved.
The French Meadows project really came about because we had an experience in 2014 with the King Fire. The King Fire burned almost 100,000 acres in the Rubicon River watershed, which is sort of the other half of the people of Placer County's water supply. And because of that, it was really a wake-up call. The French Meadows project is really an innovative partnership. And the innovation comes from not only the multiple funding sources, but the multiple expertise that those partners bring.
The 35,000 acres behind me is really the watershed for this reservoir. And it's a combined about 20,000 acres of federal land and 8,000 to 10,000 acres of private land. The private land has already started the mastication process. They started a couple years ahead of us, and then we're about to begin the federal lands portion.
Another thing that we have brought to the collaborative table is the ability to understand the effects of the thinning and burning treatments that we were proposing on fire behavior. So we've done what's called fire modeling. We've inventoried the fuels on the ground, modeled the potential behavior under given weather conditions and on this terrain in this watershed, so that we know the effectiveness of treatment in reducing fire danger. Fire is a natural part of this system. We want to prepare this landscape for the safe and effective reintroduction of fire.
Bringing back more of a historic fire regime to this landscape is going to benefit watersheds, our wildlife. That's really how this landscape evolved. And with the change that we've had over the years, suppressing all our wildfires, it's gotten a little out of whack.
In our tree marking here, we're trying to thin out the stands to bring them closer to the historic density level. In doing that, we tend to target the smaller trees first, the ones that are in the understory of taller, more dominant trees. And then we also thin some of the intermediate sized trees or medium sized tree. And the idea with that is to create gaps in the canopy, which then will break the spread of a fire up and then also create a more diverse understory habitat.
Another scientific aspect of the project is assessing the effect of forest management and water resources. Some of the watersheds in this area will be treated and some will remain as controls. Our team at the Nevada Research Institute is using ground measurements and also satellite data to assess the changes in vegetation and changes in the water balance over several years. Through this assessment, we're not only verifying the benefits of the French Meadows project, but also learning lessons that will help us extend this needed integration of water and forest management to other watersheds in the Sierra Nevada.
Our primary interests in completing this restoration project is to enhance water quality and maintain water quality, to enhance the water quantity that these reservoirs store, and finally, to protect our investment in the watershed, our infrastructure investments, as well as our recreational investments. We want these facilities, these dams, these reservoirs, these campgrounds to be here for the next generation of Placer County residents.
The work that we're doing here at the French Meadows project could easily be translated to much larger landscapes throughout California and other states throughout the West. We're bringing together the best of our private and public entities and the abilities of those entities to influence land management. And so this is a great model for expanding the effectiveness of forest management throughout the West.
Right. Yeah, I couldn't really increase the volume, so I'm sorry. I should have tested this earlier. Okay, so just to conclude the webinar, basically, tried to make like 3 points. So one is the watershed that drains slowly from deep groundwater and receive precipitation as snow are most sensitive to climate warming. And those watersheds will require most of our attention as far as the securing the future water supply is concerned. And the climate vegetation feedback remains to be one of the big question mark in terms of, how much water we will have in the future. And we really need to focus on trying to understand, the nexus between climate, vegetation, and water in the Sierra landscape or California as a whole. And based on, some of the early work and some of the work that preceded, elsewhere in Oregon and other places, reducing forest biomass can help adapt to future climate. Our modeling result actually shows that, some of the empirical data actually shows that, and it's really essential for securing our water supply and enhancing forest resilience. I didn't really talk much about the forest resilience because it's just too much to cover. But I'm happy to point on resources as far as the, how the after forest management, how the remaining trees actually function, and what's the reduction on fire behavior and things like that. So with that, thank you for your attention, and would like to leave on this positive note, because I know this is kind of a bad year, hydrologically speaking. So I'm still hopeful that, whatever a month or month and a half of winter left will reach to a good snowpack level this year. So thank you.
Thank you so much, Safeeq. That was really interesting. So I have some questions, but does anybody else who's on have questions for Safeeq? Okay, well, I'm going to say,
but before that, I just want to congratulate Safeeq. Thanks so much.
Thanks, Sam.
So Safeeq, I'm really interested in this, the feedbacks between vegetation and climate and water. And I was curious because to me, that story actually was a pretty good story. What you kind of showed with it, combining the CO2 along with the changes to climate. So I was curious, they talk about, the CO2 fertilization. Is there a moment or a time or a CO2 level, or is there a moment basically where that benefit stops being important in terms of we see evaporative demand and then ET start to go up again?
And again, that modeling exercise was a simple, one parameter, sensitivity analysis where we only modified the CO2, right? But if you are interested in more holistic feedback, you also need to account for changes in the vegetation growth, right? Because the CO2 is not only modulating the leaf conductance, but also modulating the growth rate. So I have a postdoc who is working on it, from a more using more process-based vegetation modeling, and we are seeing, somewhat similar pattern. But I think what is coming out that the ET will still go once you account for all those feedbacks. But not to the level over which people have reported in the past. So I think there have been studies, if I remember correctly, anywhere between 40 to 45 millimeter ET for every for unit change in temperature in the Celsius, I believe, which is a lot. So once you start accounting for all these feedbacks, you can bring the number to, I think it's somewhere less than 10 millimeter or even 5 millimeter, if I'm remembering correctly. So we are not offsetting completely, but the change is going to be much lower. But to answer your question more specifically, what I'm saying is so when you're looking at the RCP 4.5, when the CO2 is not, I think the current level that we put in the model is about 500 ppm. And when you reach 8.5, I think you are getting close to 800. Again, so once you are, the 500 level, then I think the change in albedo is not that much. So that's the reason why I picked 8.5, because that was the highest that you can get.
Okay.
Make sense?
Yeah, that does. No, that's very interesting. All right. Well, is anybody else who joined? I think I made a note just to introduce yourself to us so we know who is here. Oh, somebody just left, but it would be, if you want to talk to us and let us know who you are, that would be great. Otherwise, if there aren't any other questions, we really do try to end at a reasonable time. So does anyone else want to make any remarks before we say goodbye?
Safeeq, this is David Lewis. Can I ask a quick question and just say thank you for this talk?
Sure, yeah.
Yeah, so I'm David Lewis. I'm an advisor in Marin and Napa counties. And Safeeq, we've visited a little bit, but just appreciate the series. I wanted to ask you to go, you use that one experimental watershed and the harvesting as an experiment. What are your thoughts about that experiment happening pre-forest practice rules, and how forest practice rules would have influenced the results?
Yeah, that's really good question. So that was done, before the new forest practice rule came into effect, right? So that watershed was actually 100% clear cut, and followed by a slash and burn, right? We don't do that now. But what we have something similar is watersheds, right? Watersheds where you have fire that will mimic very similar conditions, especially if burn watersheds follow a salvage logging, right? So then you have 100% loss of canopy, and then you disturb landscape, right? So that's the activity that I think of. But in terms of the actively managing forest, that will be considered somewhat like an end member. That's the worst that you can expect. We are to 100% cut. So depending on like how much biomass is removing and how you doing it, you expect that your number to be less than that. So that's the worst that you can expect. Am I answering your question? But yes, we have situations where the natural followed by a salvage logging will mimic conditions practice rule conditions.
No, that helps. And we go back in history in terms of watershed studies, and we often have these extremes, whether it's just grazing and we don't get any description of the amount of grazing, or just harvest but no description or scale of it. So that's helpful, and I appreciate your next set of studies. Those will help inform those spectrums of management, the ranges of management.
Yeah. Yeah, I mean, if you have to go back and do those experiments again, we probably do it very differently. Because that's in the 1960s and this is 2020. So
no, I appreciate that. Yeah. Anyway, I'm holding you guys up.
Oh no,
Thank
this is
you.
great. No, I love the discussion. So thank you so much, everyone who joined, and Safeeq, great job, and we'll see you all hopefully next month.
All right, thanks Malika, and thanks Sam.
All right, bye-bye.
Bye.
Stop the time.